Hey everyone, and welcome. Today we're going to dive into a topic you literally experience every single day, non-uniform motion. And we're going to use one of the coolest examples out there, a skydiver in free fall, to really get a handle on the physics behind it. So what's the big mystery? Well, let's jump right in.
So, here's the big question for today. We all know gravity is a constant force, right? It's always pulling things down. So, logically, shouldn't a skydiver just keep getting faster and faster and faster forever? Why is it that they hit a speed limit, a maximum speed? That is the puzzle we are going to solve together.
All right, to get to the bottom of this, we first need to make sure we're all on the same page about the basics of motion itself.
Okay, let's break this down. Uniform motion? Super simple. It's perfectly steady. Imagine setting your car's cruise control on a long, straight, empty highway. That's uniform motion. Non-uniform motion, on the other hand, is pretty much everything else. It's real life. It's speeding up. It's slowing down. It's anytime your speed changes, which, as it turns out, is almost all the time.
And that, right there, is the key. In the real world, you almost never see perfect uniform motion because there are always these invisible forces pushing and pulling on things. Our skydiver isn't falling in some perfect vacuum. Nope, they're falling through the air. And that air, it pushes back. So let's talk about that pushing back. It actually has a name, and it's the secret ingredient to solving our whole mystery.
We call this force air resistance, or sometimes drag. Just think of it like friction, but with air. Its one and only job is to get in the way of motion. If you're moving forward, drag pushes you backward. And if you're falling down, you guessed it, drag pushes you straight up.
Now listen up, because this is the single most important idea for today. Drag is not a constant force. The faster you go, the stronger the air pushes back on you. It's super intuitive if you think about it. Stick your hand out of a car window when you're going slow. It's just a gentle breeze, right? Now do it on the freeway. The force is huge. The exact same thing is happening to our skydiver.
So, let's put the pieces together. We've got gravity pulling down with a constant force, and we have air resistance pushing up with a force that gets stronger and stronger as the skydiver speeds up. You can probably see where this is headed.
Just think about that for a second. We have one force that's constant, the downward pull of weight, and we have another force that starts at zero and just keeps growing, the upward push of drag. So what happens at that one perfect moment when they become equal?
And there it is, the moment of truth. The upward push of air resistance has finally gotten strong enough to perfectly cancel out the downward pull of gravity. The forces are in perfect balance.
And that, my friends, is our answer. It's called terminal velocity. When those forces balance out, the net force, the overall force, is zero. And what does Newton's second law tell us? If the net force is zero, acceleration stops. The skydiver doesn't get any faster. They just continue to fall at that high, but now constant speed. Mystery solved!
Okay, so how do physicists actually picture all this stuff? Well, they have this really awesome tool for visualizing these battles between forces. It's called a free body diagram, and it's easier than it sounds. Let's see how it works.
The whole idea is pretty simple. You just draw the object, and then you draw an arrow for every single force that's acting on it. And here's the trick. Longer arrows mean stronger forces. So for this book, just sitting on a table, the downward pull of its weight is perfectly balanced by the upward push from the table. The arrows are the same length, the forces are balanced, and the book just sits there. Now, let's try this with our skydiver. Right after they jump out of the plane, their speed is pretty low, so the air resistance is still super weak. The downward arrow for weight is huge compared to that tiny little upward arrow for drag. The result? The forces are totally unbalanced. There's a big net force pointing down, and that means big-time acceleration. They are picking up speed, and fast.
But once they hit terminal velocity, the whole picture changes. Their speed is now so high that the upward force from air resistance has grown to be the exact same length as the downward arrow for weight. The arrows are equal, the forces are balanced, the net force is zero. And what happens when the net force is zero? No more acceleration, constant speed.
Okay, so we've totally nailed the concept, but how do we actually run the numbers on this stuff? Let's take a quick peek under the hood and see how to solve a real-world physics problem. So check out this common scenario. Imagine you're dragging a heavy box across the floor, but you're pulling the rope up at an angle. And on top of that, friction is fighting you every step of the way. How in the world do we figure out how fast that box is actually going to accelerate? Well, here's how we do it. First, we can't use that whole 25 Newton force because part of it is pulling up instead of forward. So step 1 is to use a little trig to find just the useful forward pulling part. Step 2, we have to find the real winning force, the net force, by subtracting that pesky friction that's working against us. Once we have that, the rest is easy. Step 3, we just plug it into Newton's famous F equals ma to find our final acceleration.
And boom, the math tells us the answer. By breaking down all those competing forces, the angled pull, the friction, we can predict exactly how that box is going to move.
All right, let's do a quick knowledge check with a couple of typical physics questions, just to see these ideas in action. Okay, for the car, it gained 20 meters per second of speed, and it did it in 5 seconds. So you just divide the change in speed by the time, and you get 4 meters per second per second. For the ball, we know gravity is fighting it, slowing it down by about 10 meters per second every single second. So to get rid of all 20 meters per second of upward speed, it's going to take exactly 2 seconds to reach the very top.
Awesome. Let's tackle one last challenge that kind of pulls everything together. We've got angled forces, we've got friction, and a very specific goal for acceleration.
So for this one, we're actually working backward. We know how fast we want the mower to speed up, so our first job is to figure out the net force needed to get that acceleration. But wait, that's not the whole story. You also have to push hard enough to beat friction. So the total forward push you need is the force for the acceleration plus the force to overcome friction. And finally, since you're pushing down at an angle, you have to push even harder along the handle to get that required forward force, which gives us our final answer.
So we've really come full circle, haven't we? We started with this idea of a skydiver, and we found out that a constant speed doesn't mean there are no forces. A lot of the time, it actually means there's a perfect hidden battle going on between a force pushing forward and a force pushing back. So my final question for you is this. Now that you know what to look for, where else in your daily life do you see this invisible tug of war that results in a perfectly steady speed? Thanks for joining me.